Okay, so for each of these problems, we're going to set up an integral, evaluate the integral using technology, and our goal is an integral, but we do not want to begin with an integral. We're going to use our new slicing technique to build each integral. Okay, so number one, find the mass of a very, very thin wire that has length 10 and whose density varies along the length of the wire. So the fact that they're giving me density in grams per centimeter and they're telling me the length of the wire is 10 centimeters, that indicates I'm just working in one dimension. The only thing that matters is the length of the wire. That's why I said very, very thin. So I'm going to draw myself a picture of this wire. Very, very thin. It's 10 centimeters, so I'm going to label the left end 0.0 and the right end 0.10. And my goal here is I'm going to slice up this wire into lots and lots of little pieces. Each one is small enough that the density on that teeny, teeny, tiny piece doesn't change much. So I'm going to pick a random location along the wire, call it X sub I, and I'm going to make a slice at this location. So I'm going to have a teeny tiny slice here. And the idea is I want to let these size of these slices go to 0. So this length of my slice is delta X. So I chose a location X sub I. The length of the slice is delta X. It's very, very small. So the mass of my slice is the length of my slice times the density of my slice. So the length of the slice is delta X, and the density of the slice is the density at X sub I, which is e to the 0.1 X sub I. Length times density. And the length of this slice is very, very, very small. We're calling it delta X. So then the mass of all the slices added up, that's where I take each X sub I and I'm going to add them up, n of them. The sum from I equals 1 to n, where each slice has the mass given by this formula. So e to the 0.1 X sub I delta X. And then to get the exact mass, I take the limit as the number of slices goes to infinity. So my mass exact is the limit as n goes to infinity of the sum from I equals 1 to n of e to the 0.1 X sub I delta X. And that is the definition of an integral. That's a limit of a Riemann sum. So this becomes the integral of e to the 0.1 x dx. And my bounds of integration are going to be 0 to 10 because I'm starting at 0 and the length of the wire is 10. So I'm adding up these teeny, teeny, tiny slices at a location of 0 and ending at a location of of 10. So if I use a calculator to evaluate this, you do math 9. I'm going to integrate from 0 to 10 of e to the 0.1 x dx. So it's 17.18. And my units were grams. Okay, this time we have the density of cars down a 30-mile stretch of the New Jersey Turnpike starting at a toll plaza is given by rho of x is 400 plus 100 sine delta x cars per mile. X is the distance in miles from the toll plaza. So find the total number of cars on this 30-mile stretch of the pike. So I'm going to draw myself a picture. This is the New Jersey Turnpike. Here's the toll booth at mile 0. And here's 30 miles later that I'm interested in. I want the number of cars on here. So I'm going to pick a random location X. And I know that the density of cars at that location is given by the formula 400 plus 100 sine pi x, cars per mile. And then, so I'm going to look at a tiny, tiny slice of the New Jersey Turnpike starting at X and just going a little bit further. And this distance I'm going to call delta x, just a small, small slice of the New Jersey Turnpike. So the number of cars on my slice on my single slice here, that is going to be the length of my slice times the density of my slice. The length of the slice is delta x miles times the density, which is cars per mile. So I'm going to multiply delta x times 400 plus 100 sine pi x. So the cars on all my slices, the number of all cars on all slices, I just add up the number of cars on each slice, and I'm going to do n slices. So this is going to be the sum from I equals 1 to n. Each slice has a number of cars on it that's equivalent to 400 plus 100 sine pi x delta x. And then I take the limit as n goes to infinity. So the exact number of cars, number exact, is the limit as n goes to infinity of the sum of that, which is the definition of an integral. So this is 400 plus 100 sine pi x. Delta x becomes a dx. When you let the number of slices goes to infinity, delta x goes to 0 and it becomes a dx. And I'm integrating from 0 to 30, from the toll booth to 30 miles later. So I'm going to evaluate this in my calculator, math 9, integrating from 0 to 30, 400 plus, oops, plus 100 times the sine of pi x dx. And before I press enter, I'm going to make sure I'm in radian mode. When you're in calculus and you're dealing with trigonometry, you want to be in radian mode. And I am. So if you were in degree mode, you want to switch it. But I'm in radian mode, so I'm just going to hit enter. And I get 12,000 cars. Now I have a storage shed. It's in the shape of a half cylinder, radius 10 feet, length 25 feet, and the shed is filled with sawdust. And the density of the sawdust varies depending on the height it is at in the shed. Like it's more dense on the bottom because there's more weight on top of all the sawdust. So at a point x feet from the floor, the density of the sawdust is 20 minus x pounds per cubic foot. And I want to calculate the total weight of the sawdust in the shed to the nearest hundredth. Okay, so remember that your slices need to have approximately uniform density, and my density varies according to height above the ground. So my slices have to be at varying heights. So if I pick a height here of x and take a slice, the cross section at this height, if I slice my cylinder, I get a shoebox looking thing. This is a little hard for me to draw. Okay, there we go. And then this one kind of goes like that. Okay, so jumped a little. Start again. Okay. So I've got some height x here. I'm going to try to draw my slice, my horizontal slice through the cylinder. It's going to be rectangular. Something like this. Why does that keep happening? Okay, so I've got a rectangular slice through here. It's going to have a little bit of thickness. And it's at a height of X feet off the ground. So it might be helpful if it's hard to draw this thing or visualize it in 3D. I'm going to redraw my shoebox over here on the side. Okay, so this is my rectangular slice. The length of it is 25 feet. The height, it's X feet off the ground. So the height, my very thin thickness of this shoebox, because it's X feet off the ground, this is a very small change in X. So this is delta X. And then this distance I'm going to call R. I'm not going to call it anything just yet. Okay, so I pick a height of X feet off the ground. X. I need to know this length at X feet off the ground. So 10 is the radius. So that 10 we should just ignore. It's not the length I just drew. So I need to know this distance. So if I draw in this extra side length, that's 10 because it's the radius of the cylinder. And then maybe I'll call this third side here R. So I have a Pythagorean relationship. X squared plus R squared is 100. 10 squared. So R is the square root of 100 minus X squared. So at any height of X, I can calculate this distance, R, it's the square root of 100 minus X squared. But the length of my shoebox here is 2R. So I'm going to put that in there as 2R. So then the volume of this slice is length times width times height. So 25 times 2R, so that's 2 square roots of 100 minus X squared, times the height, which is delta X. So that's the volume, but they didn't ask me for the volume of this thing. They asked me for the weight of the sawdust inside, right? So the weight of my slice is the volume of the slice times the density of the slice. Volume in cubic feet, density in pounds per cubic feet. So the volume I've got, and then the density was given by a formula that was given. So my volume is 50 times the square root of 100 minus X squared delta X, and then the density was 20 minus 2X. Yeah, 20 minus 2X. So that's the weight of just a single slice. Then I have to get the weight of all my slices. So I take the sum, and then I take the limit as n goes to infinity of that sum. And I'm skipping a few steps here strictly because I'm out of room, not because you should. So my weight exact becomes the integral of 50 times 20 minus 2x times the square root of 100 minus x squared dx. And then I'm going to integrate from 0 to 10. The height x, smallest x can be a 0, and then you're stacking up these slices to the height of the cylinder, which is 10 feet. And then we are supposed to calculate the value of this on the calculator. Math 9, integral from 0 to 10 of 50 times 20 minus 2x times the square root of 100 minus x squared dx. So we get approximately 45,206.48 pounds. $45,206.48. 45. The density of oil in a circular slick on the surface of the ocean at a distance r meters from the center of the slick is given by the formula rho of r is 50 over 1 plus r kilograms per square meter. So we're treating this oil slick as though it's two-dimensional. Okay, so mass is going to be area times density. So our slices of approximately uniform density are concentric rings because the further we get out from the center, the density changes according to this distance r. So I have these concentric rings where density will be approximately uniform. So this ring here has approximately uniform density. Its width is delta r. So I'm going a distance r from the center and then taking a small width delta r. And then I want to imagine cutting this ring right here. Take a pair of scissors and snip it and unroll the ring. And you get a rectangular shape. And the length of the rectangle is 2 pi r because that is the circumference of the ring. And the width is delta r. That's the width of the ring. So the mass of my slice is the area of the slice times the density of the slice. And density was given by rho in this case. So the area of the slice, you think of this rectangular area, so it's 2 pi r delta r, and then times the density, which was 50 over 1 plus r. So then the mass of all my slices is just a sum where I add up a bunch of these, n of them, and each slice has the density formula for mass 100 pi r over 1 plus r delta r. I just multiplied the 2 pi times the 50 there. And then take the limit as n goes to infinity to get the exact mass. So we take the limit as n goes to infinity of all that. And that is the definition of an integral. So I'm going to have 100 pi r over 1 plus r dr. And then I'm integrating from 0 to, because that's the center, the smallest r can be is at the center of the circle. And then the outermost, they said we're going to go from 0 to 10,000. So when you put that into your graphing calculator or another piece of technology, we should get approximately there we go. We should get approximately 3,138,699 kilograms. Okay, this last one is very much like the previous. It says when an oil well burns, sediment is carried up into the air by the flames and eventually deposited on the ground. less sediment is deposited further away from the oil well. And suppose that the density in tons per square mile at a distance r from the burning oil well is given by 8 over 1 plus r squared. So we want to find the total amount of sediment in tons, that is a weight measurement, within 100 miles of the well. So here's the well, and then within 100 miles would be a circle around the location of the well. And the further away you go, the more the less sediment is deposited on the ground. So I'm going to have concentric rings where the density of the sediment is approximately uniform. And when I unroll that ring, I get a rectangular shape here. The length of it is the circumference of the ring, 2 pi r, and the width is the width of the ring, which is delta r. So the weight of my slice is the area of the slice times the density of the slice, which I will name delta. The area of the slice is 2 pi r delta r, and the density of the slice is 8 over 1 plus r squared. So then I need to add up the weight of all my slices. So it's just the sum from I equals 1 to n of 2 pi r. Actually, I'm going to simplify this a little bit. I'm going to multiply that 2 pi r times the 8, so you get 16 pi r over 1 plus r squared delta r. And then my weight exact is the limit as n goes to infinity of this sum. And that's the definition of an integral. So I'm going to integrate 16 pi r over r squared plus 1 dr. And I'm going to integrate from 0 to 100 because they asked find the amount of sediment within 100 miles of the well. So r is going to go from 0 to 100. When you put this in a calculator, you get approximately 231.5 tons. Right, number 6 is saying that each of the integrals that we set up in questions 1 through 5, we used a calculator to evaluate them, but you can do them by hand using one of the techniques of integration that we've learned this semester. So we're going to go back and evaluate each integral by hand, and we can check our work by comparing to the calculator answer. So the integral we needed to evaluate for number 1 was the integral from 0 to 10 of e to the 0.1 x dx. So I need an antiderivative of e to the 0.1 x. So I need a function whose derivative is e to the 0.1 x. So e to the 0.1 x doesn't quite work because the derivative of e to the 0.1 x is e to the 0.1 x times 0.1. So I need to put a 10 in front here so that when I do the chain rule, I get a 1 over here. So I have 10 e to the 0.1 x evaluated from 0 to 10. So that is 10 e 0.1 times 10 is 1 minus, now I'm going to plug in a 0. So I have 10 e to the 0 is 1. So this is just 10e minus 10, which I should make sure on my calculator. 10 e minus 10 is 17.18, which is what I got as my answer to the integral. Okay, number 2, the integral from 0 to 30 of 400 plus 100 sine of pi x dx. So I need an antiderivative. So the antiderivative of each term, when terms are separated by addition, you can integrate term by term. So the antiderivative of 400 is 400x. And then the antiderivative of the sine function is negative cosine. The function whose derivative is sine is negative cosine. So this becomes, the 100 comes along here. I need to make it negative. And this is cosine of pi x. But then if I were to take the derivative of this, negative 100 cosine pi x, I would get negative 100 times negative sine, so my negatives cancel, of pi x times pi. So I still need a pi here. So I'm going to put it right here. So negative 100, oh, I need the over pi to make the pi's cancel. So this will be cosine pi x. Change that to just a minus. And I'm going to evaluate that from 0 to 30. So that means first plug in a 30. So I have 400 times 30 is 12,000. And then if I plug a 30 into my next term, I get cosine of 30 pi. And the cosine at multiples of pi is 1 or negative 1. 30 is a multiple of 2 pi. So the cosine of 30 pi is 1. And then if I plug in 0, 400 times 0 is 0. And the cosine of 0 is 1. So this is minus 100 over pi again. So my 100 over pi's cancel. I have negative 100 over pi minus negative 100 over pi. So those go away. And I just end up with 12,000, which is the answer my calculator gave me. Okay, this one is really hard. I'm going to make a separate video. I'm going to come back to this one and do a separate video. Number 4. I pulled the 100 pi constant out of the integral, and I need to integrate r over 1 plus r. So you were given a hint in number 6. It says you can rewrite r over r plus 1 as 1 minus 1 over r plus 1. So I've still got my 100 pi here, and this is the integral from 0 to 10,000. And instead of r over 1 plus r, I'm going to rewrite that as 1 minus 1 over r plus 1. So you can see why that works, because 1 is the same thing as 1 plus r over 1 plus r. And then the numerators would stay the same when you add two fractions, and you add the numerators, and they would add up to r. Okay, so now I can integrate term by term. So this becomes 100 pi times, okay, so the antiderivative of 1 is r, and the antiderivative of 1 over r plus 1 is ln of r plus 1. So I'm evaluating from 0 to 10,000. So I have 100 pi times, when I plug in 10,000, I have 10,000 minus the ln of 10,001 minus, when I plug in 0, I get 0 minus the ln of 1. And I'm going to have a calculator evaluate all this for me. Okay. 10,000 minus the ln of 10,001. All right, and then I need to add the ln of 1, which is 0. I should have known that off the top of my head. And then I have to multiply that times the constant out front, which is 100 pi. Not 10 pi. There we go. So that comes out to 3,138,699. That is the answer I got when we integrated using the calculator. Okay, number 5. 16 pi I pulled out of the integral, and I'm just going to evaluate the integral from 0 to 100 of r over 1 plus r squared. So because the derivative of r squared is 2r, so the derivative of a piece of my integrand also shows up in the integrand, I'm going to use u substitution. I'm going to let u be 1 plus r squared, which means that du dr is 2r, which means that dr is du over 2r. Okay, I am just going to do the antiderivative of r over 1 plus r squared dr without any bounds of integration, and then I'll go back and do the definite integral. So this becomes r over u times du over 2r. The r's cancel, and integral. This becomes 1/2 the integral of 1 over u du, which is 1/2 ln of u plus c. Okay, so now I can go back to my definite integral. First, I got to plug in my u. This is 1/2 the ln of u was 1 plus r squared plus c. Now I'll go back to the definite integral now that I have an antiderivative. So I've got 16 pi times the integral from 0 to 100 of r over 1 plus r squared dr. Now I just have to take the antiderivative and plug in the bounds. So this is 16 pi times the antiderivative of r over 1 plus r squared is 1/2 the ln of 1 plus r squared, and I'm going to evaluate from 0 to 100. Okay, so 16 pi times, plug into 100, and I have 1/2 times the ln of 100 squared is 10,000, plus 1 is 10,001. And then when I plug in 0, I get 1/2 the ln of 1. The ln of 1 is 0, so that's 0. So now I'm just going to use my calculator to do this last step. So I have 16 pi times 1/2 times the ln of 10,001. And I get 231.48, which is the same value the calculator came up with when I integrated using technology.